Hello everybody, and welcome back to the Epic Flight Academy. I'm your host, Mike Thompson. This is our instrument rating course. Remember, to be successful, number one, you're studying this course in Epic's online instrument rating course. Number two, you're watching these videos. That's fantastic. And number three, you are reviewing all of this content one-on-one with your flight instructor. So our topic today in our instrument rating course is weather theory. Now, this is important because if you think about going to work and going to the office, your office is the cockpit of the aircraft and you are up in the atmosphere. Now, living and working in the atmosphere, we need to have a very solid understanding of meteorology. That's why it's so important to have the theory as a solid background, and then we start talking about specific products and situations. So let's begin with that. Now, you've already learned about and heard us talk about the layers in the Earth's atmosphere. Now, we frequently talk about there being four layers: the troposphere, stratosphere, mesosphere, and thermosphere. And you're probably aware, actually, there are five. That outer layer is called the exosphere. You're also familiar with the composition of the atmosphere. We say that it's approximately 80% nitrogen, 20% oxygen. Well, remember, if you look in the FAA's Advisory Circular Aviation Weather, you will find a chart that tells you specifically what the percentage of each of those gases are. Nitrogen, about 78%, oxygen, 20.9 or almost 21. So refer to that chart for those specifics. Now, the troposphere, which is the lowest layer closest to the Earth's surface, can vary in height depending upon your latitude. As you might guess, the troposphere is thicker near the equator and thinner near the poles. The majority of our weather occurs in this layer. Why? Because moisture is trapped from going any higher into the stratosphere, and this boundary layer is called the tropopause. So, where do weather patterns really come from? Well, it all boils down to the uneven heating of the Earth's surface. Now, this is caused primarily by the angle at which the sun's rays hit the Earth's surface. You can see that in this diagram. And of course, we have talked about it earlier. Near the equator, those rays are more direct. Near the poles, that same quantity of sunlight rays is spread over a larger geographic area. That causes uneven heating and uneven distribution of energy. The second reason or source really is that different masses, land masses and water masses, heat and cool at different rates. Land, of course, heats up faster, cools faster. Water heats up slower, cools slower. So this uneven temperature, this uneven distribution of energy causes these circulation patterns. In this diagram, you see an extremely oversimplified diagram of the circulation patterns that shows the air rising at the equator and sinking at the poles. Now, I want you to understand global circulation in a little bit more detail, and that's why we're going to send you back to our private pilot video 11.2, global circulation. Now, when you go back to 11.2, you're going to see that circulation pattern generally cycles at about 30 degrees and again at 60. So you remember, as you review that video, we have the Hadley cells, the Ferrel or mid-latitude cells, and the polar cells. Now, in addition to global circulation, there are also local circulation patterns. So we have what we call macro circulation, circulation on a large scale. Well, there's also micro circulation, circulation on a smaller scale. Uneven heating, again, is what causes these local circulation patterns. And here you can see a diagram of a sea breeze, where during the day, the land, of course, heats faster, the air rises, the water is cooler, so the air descends, and you see that cycle starting to happen. That's a micro circulation pattern, or we call that local circulation, or during the day, a sea breeze. At night, of course, the reverse will happen, and we'll have a land breeze. You can see both of those depicted here, the sea breeze and the land breeze. Now, this is critical for pilots to remember, because in this diagram, it shows my approach path coming over an asphalt parking lot. Then I cross over a retention pond or a small pond before I get to the approach end of this runway. Now, we want a stable approach, typically 3 degrees, but as you can see in our diagram, the local circulation pattern, that local thermal activity, is going to be rising over that parking lot and sinking over that pond, and it may cause my aircraft to fly the path that's shown here, unless I'm ahead of the game, I understand some of this theory, local patterns, and then I correct for it on the approach. Also, remember we had talked in an earlier video about convergence. Consider what happens in Florida every single day. We have air coming in from the Gulf of Mexico and from the Atlantic Ocean. And you can see in this diagram that air converges, and when it does, it rises. This causes some localized or micro circulation patterns. Now, the next major thing to review and be sure we understand about weather theory are pressure systems. Here you can see an example of the surface analysis chart where you see the blue H's and the red L's for high and low pressure areas. How exactly does that happen? Again, those pressure areas are from the rising and sinking air. The rising air causing a center of low pressure, that's the red L's. The sinking air causing an area of high pressure, that is the blue H's. So these pressure systems are a result of uneven surface heating. And the characteristics of these pressure systems are pretty clear. We know that nature will make an attempt to equalize that pressure, so air will always flow from areas of high pressure to areas of low pressure. And oftentimes we can characterize that or picture it with the use of water. So you see in these two cylinders, the high pressure wants to flow through the tube there and equalize that water level in the tube shown on your right. And that's exactly what's happening in the atmosphere. As the air moves from high to low pressure, you are going to see some both macro and micro circulation patterns, and you're going to see in a moment that those pressure differences are the primary reasons that cause air masses to move, and when air masses move, they create what we call frontal systems. Now, let's discuss for a moment atmospheric stability. Again, we have discussed atmospheric stability in detail in the private pilot course in video 11.5. The stability of an air mass depends on its ability to resist vertical motion. Stable air or a stable atmosphere resists that vertical movement, while an unstable air mass can lead to convective activity, extensive vertical cloud development, and with that, we typically see severe weather. Now, let's come back to these frontal movements. As we mentioned, it is changing pressure systems that are the main causes of frontal movements. Now, a front is defined as the front end or advancing edge of an air mass that will soon replace the existing air mass and spread over a specific region. So, you know from your earlier studies, there are primarily 4 different types of fronts, and we're showing those here. The cold front, the warm front, stationary, and occluded fronts. Here is a beautiful cross-section of a warm front. This is an air mass consisting of warmer air overtaking an area of colder air. A warm front is typically of lower pressure and higher temperature of the air mass that it is invading or overtaking. This means that the air will gradually climb up and over the top of the cooler air in front of it. You can see that in the diagram. As a result, we have warmer air aloft. Because of that, this air is more stable. So this leads to conditions associated with the warm front, and that is stable cloud types, lower ceilings, lower visibility due to rain, haze, and or fog, wide areas of showery type precipitation, higher temperatures, and lower pressure behind the front. The next common front is the cold front, and you can see that cross-section here. Notice in this case, we have cold air moving to take over a warm air mass. Now, this brings in colder air aloft. A cold front is typically of higher pressure and lower temperature of the air mass that it is invading or replacing. This means that the front will have a lot of force and aggressively cause vertical motion. Now, when this warm air is pushed aloft by this cold front, it is going to experience colder air. And again, going back to our video on stability, that will lead to unstable air masses and the conditions associated with a cold front. Convective activity, thunderstorms, squall lines, low visibility due to localized heavy rains, turbulence, and instability. The next type of front is a stationary front. Now, a stationary front is a frontal air mass, warm or cold, that simply just runs out of energy and stops moving. Now, the predominant reason for this is that the pressure on both sides of this front are starting to gradually equalize, and the air masses stop their movement, and we see what's called a stationary front. The conditions associated with a stationary front are typically poor weather conditions, and those will exist until there is some pressure difference or some type of circulation pattern that is going to cause those fronts to move on. And then finally, we have the occluded front. Now, the occluded front is a frontal air mass that overtakes another frontal air mass heading in the same direction. So in our example here, we see a warm front moving to the east. And behind it, we see a cold front moving to the east and overtaking it. Now, on the diagram, where that cold front has overtaken that warm front, you see that depicted in purple with alternating half circles and triangles. Typically, occluded fronts are cold occluded fronts because it's most common for cold fronts to move faster than warm fronts. The approximate, and these are very approximate, folks, speed of a warm front, pretty slow, maybe 10 to 25 miles an hour. The cold front, on average, usually faster, 25, maybe 30 miles an hour. The conditions associated with this included front, ahead of the front, you're going to get conditions of that warm front. Where the fronts meet, you're going to get conditions associated with the cold front. Now, before we leave the topic of weather theory, let's be sure to touch on thunderstorms. These are one of the most hazardous weather conditions that a pilot can encounter. Now, the best way to avoid them? A thorough pre-flight and a thorough weather briefing, understanding where and how these storms come from is very helpful. Now, you already know that there are three ingredients or requirements for a thunderstorm to form, and that is, as we discussed earlier, unstable air. Number two, there must be some moisture present. And number three, some type of a lifting force. Now, as we saw earlier, a cold front could act as the lifting force. There may also be what we call an orthographic lifting force. Wow, that's a pretty big word. The heck is orthographic? What that really just means is geography. I want you to think of a mountain range. So the air mass moves towards these mountains and is lifted orthographically or by the geography of those mountains. So if we have these three things, unstable air, moisture, and a lifting force, we may very likely get thunderstorms. Now, as you recall, the life cycle of a thunderstorm has three parts. I want you to review this in more detail with the advisory circular and your flight instructor. Those three parts are the developing stage, and notice in our diagram, we see the cumulus cloud developing into the towering cumulus cloud and unstable air conditions. The second stage is the mature stage, and I want you to notice in this diagram, in the mature stage, we have both strong updrafts and strong downdrafts. And then finally, the third stage is dissipating. And notice this is predominantly downdrafts. The thunderstorm is running out of energy, moving to the end of its life cycle. Now, before we leave the topic of thunderstorms, I want to brainstorm a little bit. I want you to sit down there and think with me for a second. What are some of the absolute worst possible weather conditions I can imagine? Well, let me see. How about tornadoes? Whew, that's pretty bad. Violent wind shear? Yeah. Microbursts? Whew. Hail. Yeah, hail. Yeah, that can be pretty severe. Lightning? Icing, heavy rain, gusty winds, severe turbulence. Guess what, folks? We just made a list of the conditions that you as a pilot will find with thunderstorms. Now, a microburst is a localized column of sinking air or a localized downdraft. You can see a nice photograph of a severe microburst here and this picture from the PHAC. This localized column of sinking air within a thunderstorm is usually less than or approximately 2.5 miles in diameter. A microburst is often associated with wind shear. These last 10 to 15 minutes and can cause airspeed shears of 30 to 90 knots. Review that with your flight instructor. A wind shear is a change in wind speed and or direction over a very short distance. It can occur either horizontally or vertically. Now, no discussion of weather theory would be complete without a review of dew point and clouds. The relationship between dew point and temperature defines this concept of relative humidity. The dew point given in degrees is the temperature at which the air can hold no more moisture. When the air is reduced to the dew point, the air is completely saturated and the moisture begins to condense out in visible forms such as fog, dew, frost, clouds, rain, or snow. Now, when we talk about fog types, fog will form whenever the dew point and the temperature come together. Now, I want you to take a look at our graphic, and we're showing 5 very common types of fog. Radiation or ground fog, number 1. Valley fog, number 2. Advection fog, number 3. Upslope fog, and then sea smoke or steam fog. Now, as you review these fog types in your textbook and with your flight instructor, I need you to recall one of 2 things has to happen. Either the temperature comes down or the dew point goes up. Now, when you look at these 5 examples and review this with your flight instructor, you're going to see that in each example, one or the other of those is happening. The temperature's dropping or the dew point is coming up. And in some cases, both the temperature drops and the dew point comes up. When those reach the same level, folks, fog. Well, that is our review of weather theory for the instrument rating. Join us next time.